Hello, this will be my video to explain if what we have implemented slash what is written in the book is an algorithm that will always find the shortest path. And just for clarification, I'm gonna make the assumption that the book and the kind of skeleton code that we were given for the lab are like exactly the same. So the book from pages 208, 214, how they all describe that algorithm is exactly what was implemented into that skeleton code. So let's start off with the answer. I think no, the current algorithm we have is not the shortest. I think it does not have any way to check for that, and it will just kind of give off a flight path regardless if it's the shortest or not. And here's my explanation. So the reason why I think that our current algorithm does not give the shortest flight path every single time you implement it is best demonstrated by using a diagram here. So let's say we start off at A. So okay, A is our origin, and we want to go to G over here. Okay, so since A is the origin, we're going to put on a stack A, and we're going to put a little tick for visit. Then let's flip of a coin because it's all random. We happen to go to B. Okay, so now we're here at B. Put on a visited check for that it's visited. Go to C because it's the only path to go to. Check that put the little check that it's visited. Go to D. Put the little check that it's been visited. Well, D doesn't go anywhere else. So D doesn't go anywhere. We want to backtrack now. We go to C. Well, C can go to somewhere, and that's D, but we already visited it. So reality can't go anywhere. So erase C. Go to B. Well, B can go to C, but it's C's already visited. So backtrack, take out B. Now we're back at A. A does have another path it can to a city that it hasn't visited. So we go to E. Let me put my little marker on. So we go to E. Okay. Then we go to flip of a coin, go to H. H only has one way, so it goes to I. I only has one way, so it goes to G. Well, our current algorithm will check every time we add a new element to the stack, we'll check if it's the destination city. If it is the destination city, boom, done. Program's over. We now have our flight map. Well, as you can clearly see by this diagram, this is not the shortest. We're stopping at an extra city, as opposed to if we went from A to E to F to G. That only has 4 elements, while our other one has 5. Our algorithm does nothing to check for this. It just, as so long as the destination city appears at any point, boom, stack. Or that's our flight map, we're over. We're not going to do anything more and we're done. So that's why it doesn't actually, there's nothing inside the algorithm to now be like, okay, what happens if we took a different approach and kind of basically look at all possible paths, all roads, all flight directions we can go to, and then after creating, say, the 2 flight maps, like right here, it then will check the amount of elements inside each flight path and be like, well, 4 is less than 5, therefore this is the shortest path. And this is what I'll do. So, well, this isn't a part of the grade for this answer. Kind of quick little way to kind of change the algorithm so it would work is first we would add in that edit. First, what we would do is we'll add in an edit to the algorithm that like the flight map function that that checks to see if it that the flight map it makes if it has already been made before. How that will be, and then if so, try another way. How that'll be implemented, and it's not part of the grade, so it's kind of just more thinking. That could be, using the visited strategy and doing something like kind of stuff with that to make it work. But what you kind of do, kind of a general pseudocode gist, is you'll make a vector of flight maps. So these are all possible flight maps that can go in here. Then you have your function flight map. Run it once. You want to check now. So now check this return. Check the return of this, of the function flight map. Check if it has a stack of 0 elements. So what happens is if we were to have an origin city that could never get to a destination city, the stack would have 0 elements in it. So if it does have 0 elements, then say sorry user, there's no way to go from the origin city to destination city. It's impossible. So sorry user. That's kind of your base case if you want to think about it. Then now for if there was a flight map that was created, you could get from the origin city to destination city, put it into the flight map sector. So now we have contained. Then we have this while true loop where we run the flight map function again. If this flight map's function is 0, we want to break this loop. If it isn't, then push back the flight map function's return back into our vector of flight maps. And then keep on running until eventually we will get a break. And then it'll break, it'll cut the while loop. Then you do a function that reads all the flight maps to the user. Well, we don't need this because we're picking the shortest flight map. My bad. So we just have a function that checks the size of all flight maps and picks the one that is that has the smallest elements in it. And then if there's 2 flight maps that have the same amount of elements, flip a coin. Random, this algorithm isn't it's supposed to be a simple algorithm. So flip a coin, ask the user, do whatever. But basically have a function, you'll check all the flight maps, and then it'll return ending the program. So basically you can think of the flight maps vector as like a file, one of the vanilla files that you have in like real life, and then flight map, the return of the flight map as like a piece of paper with the actual flight map drawn out. And so you're creating this folder of all these flight maps. And then once you've checked every possible path to then create as many of these flight maps, many pages of flight maps as possible, you then, now that you've created all of them, and you know these are all of them that can exist, you then check each map to see which one's the shortest. And then you pick out that page, that's the page you'll hand over to the user. But yeah, I guess to just wrap it up, current algorithm we have is not the shortest. That you need some sort of function you need inside your program to store a place of all possible flight maps, go from the origin city to the destination city, and then you need to keep on reiterating that function that creates flight maps. You need to keep on reiterating it until it is impossible to create any more flight maps, any more different ways. Because what is it? There's I was about to say a statistics term for it. Difference between combinations and it's the word for if the order matters or the order doesn't matter. But you need to create all these flight maps, and then you need to then check the size of each flight map. And then from there, because now that you have a list of all possible flight maps, you know how to pick the shortest one. But there's nothing like that in that code. It just simply makes a flight map. And if it can, it can. If it can't, it can't. And that's it. Doesn't do anything more than that. So yeah, that's the end of the video.